Hello, everyone. This has been mildly anticipated, I guess. Uh, Mildly because, it's taken a few days, and also because, in particular, question 5 is really hard. We'll talk about question 5 when we get there. But first, I would just like to comment on the overall SMO open paper for this year, for round 2, 2025, that is. I think the best description I can give for this paper is just basically a giant tick. Where a giant tick represents the difficulty level of the 5 questions, right? The difficulty basically goes 1, 2, 3, 4, 5. This is probably the best description I can give of the paper. It is fairly weird that the difficulty is as such. And I am going to respect that difficulty level as being maybe not as bad as having like 1 easy and 4 hard questions, but it's a little bit, of course, misordered, among other things. So I'm going to start off with what we would definitely agree is the easiest question, which is problem number 3. Now, there's some of you who, of course, might have overthought it a little bit because it's question 3. This is simply not hard. And it is one of those things where if you try to meta solve it a little bit too much, you end up with some problems. So it's the SMO open, but the SMO has also proven themselves to be a bit erratic in their difficulty, right? So even if it's question 3, do not assume it's in order of difficulty. Just solve it as if someone gave you this problem. And what you should do, which also applies to all of these questions, is sort of start from the easiest possible explanation that comes to mind, and then slowly just elevate from there. So for this one, I would take it literally. 4-digit positive integers n, such that fn equals to n, where a and b are the numbers formed by the first 2 and the last 2 digits. Fn is supposed to be equal to n, where n is 100a plus b. There isn't really anything particularly difficult about doing this just by manually checking 4-digit squares. So if you did a manual check, that's not wrong. If you decided that I will do something first, like let's say mod 9, and then check, sure, that's fine too. So as long as your final answer is correct and you have explained how you checked everything, it doesn't matter how clever it is. So like this is a problem where you should definitely solve it at some point. Now, the fastest way you can do it, because of the fact that you have got a plus b and 100a plus b, if you expand it, nothing much happens. So the fastest way is you can take mod 99. Or equivalently, of course, if you just take a plus b squared minus a plus b equals to 99a, and then you said that this is a multiple of 99, obviously that is an equivalent statement. So a plus b squared is congruent to a plus b. If I let this be x, then you are just going to have x and x minus 1 must contain the factors of 99. And so your cases are that your x and x minus 1, the factors that they contain are together or 1 each. This is very oddly reminiscent of the junior question from this year, right? It is oddly reminiscent of the junior question from this year, and Funnily enough, as I have shared with some of you, this exact question is actually something which I independently proposed for my March holiday class for junior. I can show you as just to prove that I am not making this up. This was the question which I put in my junior mock paper for March this year. If any one of you are wondering, so was I the one that proposed this to the SMO? The answer is no, I did not propose this to the SMO. There's no overlap between my classes and what I will propose to the SMS. It's just that this is a really obvious question to ask because it's where you can get the number 2025. So it just turned out that it was a nice enough question, just that maybe I wouldn't call it open level, right? Because this one would just give you x is 99. This one would give you x is 1 or 100, which clearly fails. Remember that a plus b squared is supposed to be a 4-digit number. So that will give you a range from 32 to 99. The one where 9 and 11 are in these two places would give you x is congruent to 45 mod 99, so 45, and then this one would give you x is 55. All of these would work and give you 9801, 2025, which is where the problem comes from, and 3025 respectively, and you can check that they all work. I'm not going to dwell too long on a question like this because we know that question 4 and specifically question 5 are coming later. I have prepared written up solutions just like the junior and senior round 2. You can find them in the description below. So if you want to see how it can be written more rigorously or systematically, along with some of my other comments, feel free to refer to that. Right? So just for here, it is not a difficult question. And I believe that most of you who took open round 2, unless you somehow just did not read question 3 for a weird reason, I'm sure that you would have solved this. So we will go this way, and then we will go backwards. 1 and 2 are kind of similar in difficulty on average, but depending on your comfort level with either like geometry for Q1 or algebra related stuff for Q2, you may find one or the other to be easier. Just a note for question 2, which I will do first because I mentioned the tick mark, and so I claim question 2 is a bit easier. On ALPS, the question is quoted as has exactly 2025 to the power of n. That is true. From what I understand, the question that you guys got if you took open round 2 is at least 2024 to the power of n. I feel like exactly 2025 to the power of n is slightly more revealing in terms of the fact that it pushes us clearly in an induction direction. But in terms of the eventual solution, they are basically the same. So I'll stick to my understanding of the problem statement. The problem and solutions are also both in the description. So this is the statement which I have seen as what was given on the contest date. Okay, so I mentioned induction. There is no question that 2024 to the power of n or 2025 to the power of n gives you some induction kind of vibes for a very simple reason that if let's say that I have got P has degree 2025, that means that Px equals to R has 2025 roots with multiplicity and not necessarily real. Okay, so this is important. You cannot just claim to me that, oh, so this will have 2025 roots. That means that if let's say that Px equals to 2025, I have got x equals to R1, R2 to R2025. Then after that, I will say that, oh, so that means that ppx equals to 2025 means that this p of x must be equal to r1 or r2 until r 2025, and then therefore each of these will give me another 2025 roots, and same for this, therefore we get 2025 squared roots and so on. That's the idea. But if you just said that, I don't know how many marks that would be worth. Probably not 0, but the question is not hard enough that this is considered a minor error, because this is missing a major part of the logic. So this may give you 2 marks if you just said this. The issue as highlighted is that how do we know there isn't repeated roots, right? Then that would not deal with distinct. How do we know that they are all real roots? That's the other part of it. So literally the 2 things that I mentioned, which is distinct and real roots, are both the main issue for this question. But it is a good idea when solving questions to try to come up with, let's say, what I would call a persuasive fake-solve. A persuasive fake-solve means that what would be something that, if let's say you don't think too hard about it, mostly makes sense. And then after that, see if you're able to clean up the details. Sometimes you can't, then we have a change of approach. But for this one, it makes sense. So what I need to do is to try to understand why are these real roots. And to understand why are these real roots, it's also not a coincidence that this polynomial is very nice, right? So it means that I kind of know how the shape of the polynomial is. Now the graph of px, you know that there are going to be roots at, well, 0 to 2024. And you know that when it goes to infinity, because this has a leading coefficient of 1, it's monic, you know that it will just go to infinity. Also, if you just think of its derivative, you know that it will more or less be just a very large derivative everywhere too, except at the stationary points, it's going to have a very sharp turn. So it's kind of like, it just goes almost as it were like this. When x is less than 0, all of the 2025 factors are negative, so it will sort of just do something like this, like very sharp turns where it, to all intents and purposes, is as if the peak is nearly at infinite size compared to a constant like 2025. And so 2025 can sort of be said to be here. And this would give me all the roots. And if you see it like this, it's sort of like a line that is connected to each of 0 to 2024. Near to it, there is a root. And then, if it is near to them, it means that the roots themselves are still in that rough interval from 0 to 2024. Which means that we can go again, right? The new roots are going to be close enough that the same logic applies, right? Because if let's say this instead of 2025 were 5, to all intents and purposes, the same drawing still works. And so all I need to do is to explain this, 1, and 2, just state my induction properly. Okay, so first justification is that I just want to say that all the roots actually come in like, now instead of saying something close to 0, something close to 1, because I don't feel like bounding too tightly what close means, and it's not important. I'll just say 0 to 1 will have 2, 2 to 3 have 2, and so on until, let's say, the final 2022 to 2023 have 2, and then because the original question statement is at least 2024 to the power of n, I will just ignore the last one. If the question said 2025 to the power of n, I will include that, but for now I can just ignore it. So therefore, if I am going from 0 to 2024, and I want to justify that the roots are down here, I just need to say a couple of things which are quite easy to justify, which is that so p is greater than or equal to 0 in the intervals 0, 1, 2, 3 until 2022, 2023. That would give me a total of 1, 0, 1, 2 intervals. And the second is that p is very big at the halfway point. Now this is pretty obvious because you're just saying that if I were to, let's say, substitute in 0.5, right? Then if I ignore the negatives, it's just 0.5, 0.5, and then after that 1.5, 2.5 until 2023.5. This is very, very obviously going to have a magnitude that is far larger than 2025 or anything I care about. So by this much larger than 2025. So that means the intermediate value theorem will tell me now intermediate value theorem it popped up in senior round 1 this year, right? It's technically a calculus concept, but it is so obvious that nobody ever really calls this calculus. It relies on the fact that the function is continuous. So that is clearly true of a polynomial, right? So that means that there exists a root in 0 half. And when I say root, it exists a root of px equals to c, where c can be anything up to 2025. So I'll just put excluding the 0. I know that that's going to be an issue. So 2, 2.5, 2.53, and so on until 2022, 2022.5, 2022.5, 2023. Okay, so now this would give me, because I split each interval into 2, there are 2024 roots. And now the induction argument will work, because my induction is that essentially you can think of it as in the interval from 0 to 2024, you start off with 2024 values. When you have got px equals to 2025, you have got 2024 roots. When you add one more layer, it means that I'm saying that p of x has to be equal to these values, and each of these values will sprout out 2024 roots that are still in that interval from 0 to 2024. Right? And so all of them will have their own ones. They're obviously not going to overlap, because otherwise you're saying px takes on two different values at the same time. So that means that you will get 2024 squared roots, and so on, where this argument is very obviously going to continue by induction. Oh yeah, sure. I should give due credit, right? From what I understand circumstantially, Q3 was proposed by my NUS High and NUS Senior Ang Yan Shen. And I understand he wasn't intending to propose this for open, right? It was actually meant as a junior question too. So let's give due credit. It is a suitable question for junior, just that it somehow floated here. And then question 2 was proposed also by my NUS High NUS friend and senior Jit Woo, who if you saw his post on AOPS, basically alluded to it being related to the Julia set in dynamics. I do not actually know what that entails. It may be some fun nighttime reading for me at some point. But clearly, no high-powered knowledge is needed to do this. It just motivates this question. It doesn't even need it to motivate the solution. Okay, now back to question 1. I'm not sure who proposed question 1, but I would say that question 1 is quite a suitable open geometry question. Except that these 3 questions are a bit in the wrong order, right? Q3 should be at Q1, 1 and 2 could be at 2 and 3. In either way, I think that would be acceptable. Again, I've included a diagram to save us a little bit of time. But many of you would have taken, well, 5 minutes, 15 minutes, 20 minutes to draw the diagram. I would say that once you try and attempt at the diagram, you will see that suppose that PCEB are concyclic is basically a condition on the triangle ABC. Right? It's a condition on the triangle because if let's say that you just drew a diagram without drawing this circle around it, but they look very not cyclic and therefore everything looks not parallel, you can tell that this angle should be equal to this angle. This is 180 degrees minus B. This here, because of the isosceles triangle, is supposed to be 90 minus C over 2. So you can equate these two in order to find a reasonable kind of like triangle configuration to draw, right? So for example, you can say, okay, I'll make B look like, let's say, now you probably don't want it to be 120 and 30, that will be too misleading. So let's say B is somewhere about 110 degrees, and then C is around 40 degrees, let's say. Or if you want like B is about 140 degrees, and then, no, that doesn't work, right? Because then C would need to be 100 degrees. Yeah, so B is like about 100 degrees, C is about 20 degrees. So for example, okay, I've taken something that is a bit closer to this for drawing the diagram, but you can use that to get the PCEB to look concyclic. Everything else is just sequential construction. So the only thing that you have trouble with in making the thing look true is the concyclic. Now, incidentally, once you see these isosceles triangles here, you will also realize that that tells you something about my triangles and lines, because this, as highlighted, is isosceles, which means that this is also by similarity. Isosceles. And you do know that this is isosceles. So PD1, E1 also isosceles. Then you have got parallel lines. So they are parallel. They do look parallel, right? If you have this, the one that we wanted to show is BE is parallel to PP1. I mean, there are no other things. They just keep drawing intersections and in circles, right? So I am sure that some nice things happen, but I feel like everything here suits a length chase, specifically ratios, because I want these two to be parallel. I know that these are parallel, and to all intents and purposes, all of the stuff are on the same line. The same two lines coming from A. So I feel like as if, okay, I'm sure that I'll be able to combine the ratios and use some power of a point argument or use length chasing in the triangles with in circles, because As we know, when you have got your just default triangle ABC and your default configuration for in circle, we know that this is S minus A. We know that this is S minus B, S being your semi-perimeter, right? And S minus C. So I see no good reason why I can't length chase it and specifically use the ratios that would come from lengths on AE1BP and AEP1C. I would also say that there are, echoes of some projective geometry kind of logic because of all the intersections and or when you've got 3 points here and 3 points there, things like your Desargues or your Pascals can come to mind. What I would say is just simply that that's not necessary, and none of the intersections except for D and D1 are currently named. So I think that we can do something simpler, but I wouldn't be surprised if some of you are able to point out some of those things. Okay, so I'm just going to write down the ratio that I want, the ratio that I know, and then I'll see what I need because I don't know what I'm supposed to get out of here. Okay, so BE is parallel to PP1. AB over AE equals to AP over AP1. Looks like this would be what I want. I have got the two green lines are parallel. That involves both B and P1. So that's good news. AE1 over AP1 equals to AB over AC. So I see that if I were to cross multiply them, AB times AP1 is a common thing. And so I'm just left that to show that AE times AP is equal to AE1 times AC. Okay, which is if and only if AE over AE1 equals to AC over AP. Now, is that going to give me another parallel line? The answer is yes. I now seem to want a third parallel combination, which is this is parallel to this. Okay, so it seems like that is what I want. I realize that E and C and P and E1 are all quite corresponding to each other. I feel like saying some sort of homothety argument, but I realize I can't. Right? I feel like saying some sort of homothety, but it's like E1 is the in-touch point of this in-circle. E is the in-touch point of the other in-circle, and then P and C, yeah, I want to say the correspondence, but this big circle is not an in-circle. It's not tangent either P or C, and I do not want to draw any more circles. Maybe I could, but feels pretty annoying. I then considered, can I say that the two triangles with in circles are homothetic? But then when I actually read again what are the triangles that I drew the in circles of and looked carefully, I realized that I don't actually need homothety, right? Because this is the first triangle, AEP, and then the second triangle, this is the second triangle. The first triangle was just triangle ABC. I realized that they're just similar to each other. Right? The two triangles are similar. They are not, it's not a spiral similarity. It's not a homothety. but they clearly share the same angles, right? There's this one here, and there is the common angle at A, which basically every triangle in this figure shares. So if they are similar to each other, then the ratios in those two triangles will correspond. And so in triangle AEP, E1 is the E in touch point. E in touch point means opposite E. In triangle ABC, E is the B in touch point. And if they are similar, and E and B correspond to each other, then the ratios on their sides also correspond. Now, I could say this by writing the S minus A, S minus B, S minus C things, but it's okay to talk about similar figures having the same ratio in corresponding things. So you can jump straight to say that, therefore, in triangle ABC, I look at how E divides it, AE to EC, and I look at how E1 divides up the side in AEP, that's AE1 to EP, to E1P. Actually, I just go straight to AE1 to AP, right? And AE to AC. And lo and behold, this is what I want. They are the same thing. So I think the main difficulty of this question is just that if you don't notice this, you would get there by a little bit of random looking length chase where it may eventually arise here, or you may get there by a long trigo bash where because of the fact that angles are equal, you will also get there, but you may not realize how it happened. It just seems like magic. So this is really a pretty nice geometry. And also I would add that it is not that easy to bash, which is disappointing for some of us, but it's also a good feature of a well-set geometry question. Okay, so that was sort of the warm-up to the main event. That is also kind of the set of 3 questions that is the upper bound of almost everyone who took the open round 2. So for anyone who did 3 questions, good job. You have done as well as can be reasonably expected of anyone. It is not to say that the other 2 questions are impossible, but I think the other 2 questions being solved are conditioned on a couple of things, which I will talk about when we now jump forward to question number 4. Okay, so question number 4, as has been circulating and as I did recognize pretty immediately, it is a question from the IMO shortlist. It was proposed by Jitru and Limjack. Backstory is that, first of all, this is one of the few questions that was proposed by Singapore to the IMO shortlist. We don't have that many top IMO participants in our relatively short history of participation, which also means that we have even fewer who are interested in setting questions, and therefore we have even fewer that will be accepted to the IMO shortlist. So this is one of the few. It is a pretty clever question. It was also a question that was basically inspired by a student's fake solve. A student basically just in some other problem claimed that it was obvious that there cannot be infinitely many such n tuples for any n. And of course, when you make that claim and say it's obvious, Definitely you're not going to get marks for that other question, but Jitwo and Limjack basically were wondering, well, so is it true or not? I mean, the fact that it is obvious is definitely false. But whether was it actually true that no n exists is not obvious. So they looked at it, and then after they found a solution, and then they proposed it, it got accepted as an N6, didn't get used in the IMO, but it's still one of the few that was accepted from Singapore's proposals. Okay, so that's the backstory. It is therefore, two things come from this story. One is that it's an N6, it's not easy. Two is that it is a significant enough proposal such that some of you may remember the question, and of that, a few of you may remember the solution. If you remember the solution, good job. But obviously, if let's say you had not seen this question before, given that question 1, 2, 3 will still take some time to solve and write, it is not surprising that you wouldn't have enough time to solve an N6 or to discover it from scratch. Okay, so let's put that backstory aside and now just try to solve the question. Obviously, n equals to 1 fails. Do you get marks for saying n equals to 1 fails? I don't think so, sorry. But maybe they give 1 mark. If they give 1 mark, you will never know. I will also never know. Someone in the SMO committee can tell us how did you score all these questions, right? I mean, I don't know how confidential it is, but if anyone who was involved in grading, observers, if you want to share, I'm more than happy to hear it, and I'm sure everyone is more than happy to hear it. But if it's not possible, then my guess is no, you don't get marks for saying n equals to 1 fails. Now, a rule of thumb in number theory is just that unless there is some reason why having more variables makes things worse, let's say by some bounding argument, most of the time, you don't need that many degrees of freedom to accomplish something. This is very vague, but I mean, as some simple examples we know, let's say Pythagoras theorem, right? You can use 2 squares to get another square. Fermat's last theorem says, oh, you cannot do it with 2, but very often you are able to do it with 3 powers to get another power. Goldbach's conjecture, of course, it's still unknown, but you are able to use 2 prime numbers to sum up to any even number. So oftentimes, you would say that if there's no obvious reason why it fails, I think it should be small. How small? You try to prove things fail until you cannot prove it easily, then most likely it can be constructed. So we can start with n equals to 2. Let's say I've got a plus b and 1 over a plus 1 over b. Or maybe because I'm working with rationals, let me not deceive myself into thinking that these are integers. I will just put this here. Now the good thing is that both of these have the same numerator, but the 2 different denominators. I kind of want to say that this has constraints. I want to sort of say that this implies that A, B, C, D must divide these, but that's not true, right? Because there can be some common factors. However, I do know that I can assume that the top and bottom are co-prime. And if they're co-prime, then I still can't combine these two because B may have a common factor with C, A with D. But I can just look at them individually and say that, all right, so B goes into here, means B must also go into here, and A doesn't help, so therefore B equals to D. But by the same logic, D goes into here, and D is co-prime to C, that's why B equals to D, right? So I wanted to say B divides D, D divides B, so they must be the same. But by the same logic, that means that A equals to C as well, which just means that the 2 fractions are the same. And if the 2 fractions are the same, then you are clearly going to fail. Right? I think we can say clearly you cannot have 2n and 2 over n being integer only works for, well, n equals to 1, half, and 2. So n equals to 2 fails. Okay, now for n equals to 3. First up, if you try to add up, it is fairly ugly. The argument doesn't work anymore. If let's say that you say that, oh, okay, so I assume f is coprime to e, d is coprime to c, b is coprime to a. I take f, this one disappears, this one disappears, this one disappears. F divides bd. That doesn't do much. F divides bd. Now I can say that this doesn't do much. I also have the fact that this is not like necessary. So this is necessary. This is not like a sufficient condition, right? Because if now b and d have common factors, then like individually b, d, and f dividing this is not necessarily enough. But at the same time, this is not difficult to satisfy, and I can't think of a very simple other reason for this to fail. Likewise, if I were to flip it around and say this, can't really think of a very simple reason for it to fail. Now, questions 4 and 5 are both going to have this same dynamic. You have to sort of take high probability guesses at what approach to take, or you have to take high probability exclusions of what not to do. Meaning that I'm not 100% sure that I have to discard this, but I am rather sure, and therefore within the constraints of contest, if it turns out that you are supposed to use this very counterintuitive approach, almost nobody's going to figure it out anyway. So I cannot see how this is going to go anywhere. If let's say that I put the reverse in, my only other thoughts of, let's say, having a proof that this n equals to 3 fails is adding or multiplying, and not much happens, right? If you add it, you might think, okay, AMGM tells me that it's at least 6, but I don't really get any contradiction at all. If I were to multiply it, likewise, I just get a big mess and I can't really conclude anything too specific because it's not less than something. If the product or the sum is small, then that's very constraining. But here I'm saying that the product or sum is big. That doesn't tell me it doesn't work. So I can exclude a divisibility argument for n equals to 3 being impossible, most likely. I can exclude an algebraic or bounding argument, most likely. And so I'm going to try to see if I can make it work. And so if I can see if I can try to make it work, it means that I'm going to try to construct. Okay, so I'll see if I can try to construct. Now, looking at this, if I am trying to construct, I must satisfy this. I don't want, let's say, all of them to be 1. Right? 1, 1, 1 is going to give me something where I know, let's say if I have a plus c plus e is integer, 1 over a, 1 over c, 1 over a integer. That doesn't work because of some bounding argument. In fact, this thing being equal to an integer, I'm sure was some SMO round 1 question. So it is definitely not going to be 1, 1, 1. There are effectively 2 different types of approaches. The first is that, let's say, A equals to C equals to E, right? This is one type of construction, but I don't want all 3 to be the same. The second type of construction is sort of like just 1 XX. Maybe I'll just say like B, D, and F. So these are the basic types. A third type, which would also satisfy this, is if let's say I had something of the form, let's say PQ, PR, QR. But I'll start from the simplest one, right? And then after that, we'll go from there. So if I were to use, like I said, ACE all equal and BDF all equal, that doesn't go very well. And so I want to see if I can mix them up. Let's just use a Y and we'll see. Okay, so it means that I've got Y over 1, Y over X, Y over X, and then 1 over Y, X over Y, X over Y. Well, I then realized that now I can't really repeat them in this way, because if I were to repeat them in this way, then I have the obvious problem that essentially this is just the same as the n equals to 2 case already, right? Two of them being equal is just as bad. Okay, so I need to find something a little bit more interesting. Maybe PQPR and QR is a little bit too general. Again, we're starting with simple, so why not just PQ, P, and Q? That's it, right? So I have the choice of mixing them up or not mixing them up. I think it makes sense to just try various of them. You will quite quickly find that if you make them all the same, it doesn't go very well. And so the next combination that you could try is something like this. Now remember that I get to choose what P, Q, and X are. Or of course, I'm able to permute this as well. I will see. Okay, so now this is how I experiment with this in terms of trying to construct. I did consider induction, but well, not quite sure what to induct on and not sure how to go from one solution to another. Right? That thought will come back in a second. Now, so this is where it helps to know your SMO history, because if you were to arrive at something like this, I mean, P plus Q are random. I want to get arbitrarily many. Of course, I could pick X to be any factor of P plus Q, and then I could choose P and Q to have factors. But really, if you just let X equals to P plus Q, which would satisfy this, you end up with this. Which, of course, if you expand out P plus Q squared, there's a 2PQ. Yeah, and this is our infamous Vieta jumping from the 2023 SMO Junior / Senior Round 2. I mean, it's also famous as the task where 1 plus P squared plus Q squared over PQ is an integer. Two things are true, right? One is that it will be equal to 3, and the other is that there are infinitely many PQ where it becomes equals to 3. it is also pretty easy to remember it. I'm not going to go over the Vieta jumping again. You can either look back at that solution or you can just search on this. This is a very classic combination. But I can just tell you what the combination is, which is that your PQs by Vieta jumping are going to be sort of like if you take your Fibonacci sequence and you just take 1, 2, 2, 5, 5, 13, and so on. These pairs will give you 3, and therefore that gives you that n equals to 3 works. Right? Infinitely many. I'm explaining how you can motivate it, but if you have never seen Vieta jumping, and not just Vieta jumping, if you've never seen Vieta jumping close enough to this, it is pretty unlikely that you'll be able to come out with a construction like this, right? That's the fact. So some questions in the SMO, you can sort of look at it and say, you know what? I'm just going to learn this and understand it for next time, because the first time there is no way that anyone is going to figure it out by themselves, right? No shame in that. Yeah, and of course, what you have all been waiting for is probably question number 5. Now, question number 4, I'd seen the IMO shortlist question before. In fact, I used it in my problem solving class for last year, right? I used it there, and so I can't pretend that I did not know the solution immediately. But of course, for question 5, I did not. And I think it's good sort of now to talk about it from a macroscopic perspective first, right? It's a good example of how the more you know, the higher the chance that you will eventually figure out the solution. But if you don't know as many things, it improves your conditional probability of solving it quickly if you have the solution idea as one of the things that you are aware of. So if you have no idea that you can do such a thing, probability is 0. It's sort of like if let's say that you have got 100 keys and 100 doors, right? It would take a long time to unlock all the doors. But if let's say that you had 1 key and 100 doors, you will probably be able to use that key faster, even though there'll be 99 doors you can't open. So for a question like this, the solution actually is not that complicated, but you will need to rule out a lot of things. This is the process I went through, and I think this is the process that many of you, if you are in like the national team or at national team adjacent, you also would have to spend a lot of time ruling out things. And so I think it's worthwhile talking about ruling out things, and in the solution notes, I've basically written down quite literally 2.5 pages of things that I tried, which sort of led to the motivation for the solution. Right? And the final solution is pretty similar to a solution that's posted on AOPS. And it is, of course, something which I would say is very difficult to come out with in a competition setting. Perhaps more difficult than coming out with Vieta jumping Q4 construction, even if you had not seen that problem before. Okay, so I'm going to sort of talk through my thought process. The first thing is this a NT or combi? Is it NT or combi? Well, because I know that this was an N, and there are no combis in the paper. Well, there was no NT in senior, we know, so we cannot be sure. There were 2 combis and no NT, but I am leaning towards it being combi for 2 reasons, right? One is the problem distribution in the paper. combis. The second is that mod m for arbitrary m is weird. Mod m is weird because of the fact that you can't split up and recombine. Meaning that you cannot say, okay, I'm going to first show it for prime numbers, then after that prime powers. How do you can't lift the exponent in any way on this. And then if you've got prime powers, I still can't combine them, because how do I know that those two numbers for this prime power and this prime power will happen at the same time? So I cannot imagine a way of splitting it up. So therefore, again, this is with high probability that it is combi. That implies that I can't rely on quadratic residues, because I know that, for example, -1 over p, your quadratic residue, -1 is a quadratic residue, is if and only if your prime is 1 mod 4. So I don't know whether a -1 will show up, let's say. Now, why may I care about -1 is because, yeah, I mean, that if you can have x squared and minus x squared, they sum to 0, right? But I don't know whether this will happen. Now, another thing which I was thinking of, can this be 0? Well, of course, if c is congruent to n congruent to 0, then that will happen. But apart from 0, 0, 2c squared minus n squared is 0, means that, yeah, 2c squared congruent to n squared, which for non-zero, if let's say I'm considering mod a prime, it's if and only if, well, it's possible if and only if 2 is a quadratic residue, which again has a different condition. So it means that I cannot rely on so-called local arguments. Right? So this was the first thing, right? It means that local argument means that these special values work. Too messy. Right? So that is the first thing that I have to rule out. Now, the next thing that I want to say is that how difficult is this in the special extreme cases? Now, the extreme cases are basically going to be that C is constant, and the second is that C keeps increasing. So you don't put any coins, or you keep putting coins. Now, I want to understand how difficult this is, meaning that is this, there will eventually be two numbers, like a very loose condition, where I can use some sort of pigeonhole or even probabilistic pigeonhole? Or is it something where it is going to be very tight, and therefore maybe it's some sort of invariance kind of argument? So, or like, coloring, that kind of thing, where it's just off by a little bit. So if I try C is constant, I realized that apart from 2C0, plus or minus, of course, and vice versa, I can't really guarantee anything else about 4C squared. Again, because of the quadratic residues, which means that there's only really like one guaranteed thing that I can use for this constant case. Meanwhile, if let's say C keeps increasing, and let's say that I let the number of coins be n plus k. So So if you try this, you realize that it's surprisingly annoying to solve. Remember, k is some constant, you don't get to pick k. This is what you get. I realized that, oh, this is irritating. I mean, if I've got 2k plus a plus b squared congruent to 2ab, I'm not that sure how to do it. And the only way, because 2ab again is like, I can choose a and b. So I could choose a and b such that it is some square. There will be parity issues again, which I hope not to deal with. So the easiest is to just sort of say, all right, I can let a be 0 so that this is gone, and then b be negative 2k. Okay, everything is mod m here, of course. So this couple of cases, both of them do get resolved. Now, it also tells me that, okay, if it is not constant or repeatedly increasing, that means that it is a mix of increasing and not increasing the number of coins. There will be some sort of discrete continuity argument. So what do we mean by discrete continuity arguments? Means that because you cannot just stay constant, you know that C will take on all values at some point. That's because you will plus one once in a while. But your plus one and plus zero also means that sometimes your n, as it goes up, C doesn't go up. So your n minus C will keep increasing over time and take on all values. Of course, when I say all values, I mean all values that are large enough. I also mean all values mod m, because if it's all values that are large enough, that covers everything mod m. So this is sort of at the back of my mind. I don't see how this is very useful straight away, but I feel like this is definitely an important feature. Now, I want to look at the condition again, which is sort of like algebraic stuff. Can I do anything like that? So I say that, all right, if let's say I've got 2ca squared minus a squared plus 2cb squared minus b squared is congruent to 0. Now, I remember the identity that tells me that the product of the sum of two squares is the sum of two squares. Now, incidentally, of course, 2 is a sum of two squares. So it's a special case, but it reminds me that I can write this as a sum and a difference of these. And this is good because it doesn't really depend on m, right? We had this issue earlier on where we said that I can't rely on number theory-based arguments anymore. So I see that these two versus these two is kind of saying that, okay, I basically will win if CA plus CB, CA minus CB is equal to AB, or A minus B, or minus AB, or minus A minus B. And I feel like this is quite significant And at the same time, I feel that this is both good and bad. The good thing is that it sort of blocks a lot, right? Because it's not just one case, it blocks many, many things. The bad thing is that, again, it depends on parity, which is a bit annoying. So then I look at it again and say, well, there's some other good thing. Another good thing is that if let's say that I wanted to say that I have this thing to be equal to this, CA plus CB equals to A. When you fix, let's say, CA and you fix A, this will happen. That means that because your C takes on all values, eventually CB would be congruent to A minus CA. So it is meaningfully going to be that one pair of them will overlap. And also, I guess, CA CB will be congruent to B will also happen. Because then that's B minus CB, which we said also covers all the values. So it's kind of good. It's kind of good that I know that this is not a meaningless condition, but it's so hard to use. This is basically where I stopped on Saturday night, meaning that so my lessons after they ended, like I said, I had seen Q4 before, so I didn't have to worry about that. So after 1 and 2 were done, and then I was looking at this. This is where I got to, and then after that I was like, okay, I'm too tired to work through this. Maybe there is some sort of nice feature that I can exploit from here. And I proceeded to like look at it the next day and realize that it is not going to really happen. So I couldn't do anything, which led me to a new idea the next day. And the new idea is I'm missing something. I feel like there is something better about this 2c squared minus n squared that I am not seeing, and I feel that doing all the algebra in the world is not going to help me to find it. So let's try some small cases. Now, when I said try some small cases, it means that draw a big table, and this is actually what I did in between my lessons / my work itself. Like, okay, let me just write down some small cases. I think I will see something. Hopefully. So let's say that we try m equals to 5. And just literally fill up the table with your 2c squared minus n squared. Just put it in. So 2c squared minus n squared, where n is 0, this would be just 0. This would be 2. 2 times 2 squared, 3. I know that there will be symmetry in here, so I don't really have that much to fill. Right, this is negative 1 squared, so that's 4, negative 4 squared, that's 1. So I only really need to fill this, and then I realized that actually technically I just need to add these, right? It becomes like an addition table, so filling this up is quite easy. A bit boring, but quite easy. So once I have this down, oh my gosh, 3 plus 1 is 3. 3 plus 1 is 4. And then after that, you can just reflect this all over the place. Now I started to then think, can I make some sort of argument about what happens in here? Then I realized that again, no. Remember that we know nothing about M, so number theory arguments are mostly bad. The symmetry is just trivial number theory, right? X squared is congruent to negative x squared mod M is all I can say. Other than that, I dare not touch it. So I have to keep on telling myself, don't try to do number theory. It doesn't work. So instead I say, okay, let me try to find a path. Now, if I want to try to find a path through this, what does a path look like? It means that I am each time going to have Cn either goes to Cn plus 1 or C plus 1 n plus 1, which means that either here or here. I say, okay, so for example, I can't actually use 3 because it both ways will fail. Now, effectively, you have got a cycle. Right? So it's sort of like if let's say that you go like this, then like this, then like this, then like this, then to here, 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 and then back to here again. That's what the cycle looks like mod 5. I want it to be that there is a cycle. I mean, I want by contradiction, is there a cycle with no residue summing to n? I mean, by pigeonhole, you know that there will be a cycle. It also means that since there will be a cycle, and then after you finish the cycle, you go again, and you go again, and you go again, I actually can ignore the zero, right? The zero is basically gone. And so I thought that, okay, is there some sort of argument now if I treat this as a graph? Is there some sort of argument about connectedness that I can make? And of course, I realized quite quickly that this is surprisingly tight. Because when I say tight, again, it's like, let's say if I just want to use ones, I can get quite far. The one comes from here to here, to here, to here. Okay, then now I use two. And then now I can use one or two. I can almost complete a loop. Now, if I were actually able to finish a loop, that means I've got a contradiction. But I can't finish the loop, right? Then I tried the same for 7, which I am going to just copy in to show you what I did for 7. Now, I chose to have 5 and 7 because one of them has basically got -1 as a quadratic residue and the other does not. So it's a little bit different. And I wanted to see how that would go. So this is the thing that I did for 7. And again, I realized that, okay, there is a long path. Because for the case of m equals to 7, now we know that when c equals to n, 2c squared minus n squared is just c squared. So it's just going to have a bunch of quadratic residues. And if -1 is not a quadratic residue, then that means that no pair of things along the diagonal, which is the quadratic residue, will sum to 0. It's just that you're not allowed to use 0. And incidentally, if let's say that I looked at this diagonal, I realized that, well, this almost works, but I'm literally not allowed to use it because if I use this diagonal here, I know that as soon as -1 is a quadratic residue, then all of these things which come from -n squared are literally the things that I'm trying to avoid, right? 1 and 6, 4 and 3, 2 and 5. Can't use them. And if I can't use them, that means that this whole column is dead. Obviously, you can't make a cycle if one whole column is dead. So then my next thought is, okay, I can't actually use the quadratic residues, and quadratic residues are all over the place for different values. Like here, I'm not even interested in the diagonal because they are 1 and 4. But am I able to talk about disconnecting it if I view it as a graph? Now, unfortunately, when we try to disconnect the graph, it is a little bit difficult to talk about disconnecting the graph because uh, how do I actually disconnect a graph when the moves I can make are like this and like this? Like what does it mean to say that I am stuck? It's not that clear, right? What does it mean to say that I am stuck? So if let's say, for example, I say that I have crossed out everything on this diagonal, I'm not really stuck. I can still move through. I mean, in this case, I can't. I know that it would never really be possible. That's what the question statement tells me. But just based on disconnecting it, like why can't I just go on some, let's say, path around it? And then I don't see any reason because I can't seem to disconnect the graph easily when the movements are like that. Until I realized that, maybe I can disconnect the graph not this way, but the other way, the other diagonal. If let's say, for example, I disconnect it by saying that nothing on this diagonal was picked. If nothing on this diagonal was picked, then I know that I can't go through anymore because my moves are only like that. And of course, there's a slight problem. The slight problem is that if I looked at every of those diagonals, there was always a pair of them of which I need to pick at least one. Because, or rather, of which I can use at least one. As I say, 2 and 5. I can't use both, but I can use one of them. Which means that I cannot say that I picked a bunch of residues and no matter what bunch of residues I pick, a diagonal will be destroyed because seemingly every single diagonal, there is a pair of things. So I asked myself, why is it like that and what's going on with these diagonals? And so I decided to check on these diagonals again and say that, well, for each of these diagonals, it's basically n is c plus x. And we have actually been through this story before, earlier on already with those n minus c, right? So it's like, okay, these diagonals are the different values of n minus c. 2c squared minus n squared, how does it look like in that scenario? So this is what we have. And then I sort of see that, it is actually just the quadratic residues. If x is a constant, it is just the quadratic residues translated. Which means that if it's just the quadratic residues translated, all the diagonals are pretty similar to each other. And when I did some of the work, I realized that, oh, actually you can see that, let's say 0 to 5, 1 to 6, 4 to 2, 2 to 0, like, they are just translated versions. So I want to use that, and I want to see it a bit better. So in order to see it a bit better, I also realized that moving along this diagonal has kind of done nothing in my attempt here because I know that I cannot just keep moving along the diagonal since that is the c keeps increasing case, which means that I need to go down. And once I go down, I'm on the next diagonal. And once I'm going to the next diagonal, I need to go through all the diagonals before I come back again. And so therefore, instead of writing it like this, and also because I know that the diagonals are just translated versions of each other, I should probably re-express it where I change my coordinates and change the table such that each of the diagonals is now a row. In other words, I read it off like this, and then after the next diagonal, I read it off like this, and I just continue that for all the diagonals. Okay, so this is what happens where after the translation, it means that now my moves are just this way or this way. That's convenient. I think it's easier to see it this way than diagonal and horizontal, right? It's kind of like a change of coordinate slash basis if you're thinking of it from a linear algebra sense. Okay, so what else do I notice about this once I have viewed it from this perspective? Well, I had those symmetries just now. So I see that, well, the symmetries are now changed from just reflective to rotational, 180-degree rotation. But not only that, I realize that this part and this part are just negations of each other. We already knew that because I highlighted here, right? One of them is just the residues, one of them is just negative the residues. But also, I realized that when we have got this grid here, yes, we do have this rotational symmetry of the zeros. But for everything else, you kind of get a nice, so it's sixes, ones are complements of each other. And if let's say that I've got the threes and the fours here, they are complements of each other. And I realized that, oh, so if 180 degrees, it is now the same. When I rotate it 90 degrees, it is negated. Of course, where now the meaning of my columns is still is a bit different. It is now n minus c. Sorry, my meaning of my rows, the meaning of the columns is still c. Meaning of the rows is now n minus c, the diagonals. So I realized that this has probably given me my best chance. Okay, when I say I realized, it's sort of like when I reached this this observation of like I should try to rearrange it with diagonals. That's where I was made aware of the AOPS solution, which is of course turned out to be exactly this. So the rotation feature is something that was, I guess, algebraically expressible here, but here it's visually clear, and it's actually equivalent to this thing from long, long ago. It's just that this has now made it actually readable in a table, because here it was so split up that I can't see anything. But now I can see how it looks like, this 90-degree rotation, and I understand that, oh, so what happens is that if you try to make a path, other stuff are blocking you. If you start to, let's say, go here, then this is blocking you. If you come down here, then this is blocking you. You come here, then this is blocking you, and then you're stuck. Okay, so then it's like, how do I actually make a path that cycles around? The path that cycles around cannot go through the center, it has to kind of go through the side. So is there a way that I can avoid it and just go through the side? Let's say, of course, I know that this doesn't work for the numbers we have because there's all these zeros in this special case. But let's say, for example, is there a way that I can just try to sneak down the edge like that? Or even just like that, and hopefully nothing goes wrong. Because if I were to look at this rotation here, there's nothing wrong with this, right? I mean, that these are the parts that are blocked, and I don't want to use number theory anymore. So in general, is it actually a problem? Yeah, and so this is the final thing that I realized that, well, I mean, I have been treating it as if the whole time we are just making a cycle within the m by m block. But we do know that because you are not going to be just increasing or constant throughout, you have a mix of the two, you will actually escape out of this block in actual values, if not mod m. And therefore, if I were to sort of expand this out, two good things happen. The first is that if let's say that you even just add one more row, then these boundaries, the rotation thing already still works. No more problems there, where the 90-degree doesn't just apply to this bottom bit and not to the top, it applies to everything. And the second is just that now if I have got a giant, let's say, I'll just draw the equivalent of this. What we're saying now is just that if I were to make some path, yes, technically I can just stay here for a while and there is no contradiction because the part that is now blocked is, let's say, down here in this. But if I view it from the entire macroscopic picture of there are so many of these, path that you're taking is going to sort of eventually, it cannot just keep on staying there, it will go down. And when you rotate this, I am not rotating this very accurately, but you know that there is definitely going to be some intersection. I also do not focus too much on the shape around that point of intersection. So the conclusion, therefore, is that it is by, you can call it different, like connectedness, you can call it by discrete continuity, you can just say it is clear that if at some point, because you go down, you will reach a boundary that is low enough where this is your start and this is your end, then when you're rotating, this is your start and this is your end, and no matter how you draw it, there will be some intersection somewhere. This is the outline of the proof, and the various components in front basically are mostly going to be a mix of things not to do, as well as why would you consider this. This n minus c and c basically pops up multiple different times as I tried different things. When I tried the special cases, when I tried to think of it in terms of continuity, in terms of an algebraic thing, in terms of the graph, and in terms of the paths, it just pops up in many different ways. As I was saying, this is something where there is a lot of time that is going to be taken to exclude the other possibilities. So I sort of think that if you were experienced with questions of this difficulty, you will exclude the alternatives faster. For me personally, most of the questions that I do currently when I'm teaching are not going to be at this difficulty. So I tried a bit more so-called standard number theory tools than would probably be advisable. If in reality you're doing questions where you can infer it is hard, perhaps you might be able to fast forward that process a little bit. Okay, so overall, this is a good quality question for sure. And I think the paper itself is not bad. It just has the issue of question 4 being a repeat, as well as question 3 being misplaced. But if you consider the set of 5 questions, I would say it's pretty nice. Okay, so if you have any comments, please leave them below. If you have anything that you don't understand, start by reading the solution that I've written in a more organized fashion. It's in the description below. And of course, feel free to leave any other feedback or just general comments of annoyance at the SMS. So thanks for watching. And for those of you who are heading to the IMO in a few days' time, all the best.